Alright, to FRQ5. Alright, so part A wants us to graph this data here using or having Hooke's law in mind. Okay, and if we remember, Hooke's law is f of spring equals kx. So what we do have in this data set is an f right here and our x, so we can go ahead and plot those values and make sure we label x's, meters. Okay, so let's go ahead and plot everything. Okay, moving on to x. Right, and we can plot our points. And there we go, we have our graph. Alright, so moving on to part B. Does the data follow Hooke's law? Okay, so remember Hooke's law of a spring equals kx. Now, if you were to move around this formula, you get k equals f of spring over x. And we know that k is a constant. Now, looking at our graph, we have this, the weight of the masses, which is a force, and we have the x, which is how much the springs are pulled. So in our graph, we have an f over k, and then we have this constant slope, which is, f over x, is equal to our constant slope, which happens to be k. So the data set does follow Hooke's law. All right. So now moving on to part C. Okay. If a 0.8 mass is used, how far will it stretch the spring from its initial position? Okay, so let's go ahead. So we are going to use F spring equal to kx. Now, we run into a problem, however, because yes, we do in fact have our force, but we do not know k, nor do we know x, because that is what we are trying to find. So what we can do is, using this idea, we can find our k to then plug into there. So we can just pick any data set on here. Let's just use the first one. So f is going to be 0.98 and our x is 0.025. Alright, plug that in to calculator, and our k equals 39.2 newtons per meter. Okay, so now for our force, that's going to be the mass times gravity. And then we have our K of 39.2, and then X, which is what we are trying to find. Alright, and we get 0.2 meters for our X for part C. Okay, so moving on to part D. Alright, on to part D. So it wants us to use the first data set, and that weight is being pulled an additional 0.082 meters from the equilibrium. And then it wants us to use energy to calculate the speed or the mass at the instant it reaches equilibrium. Okay, so let's go ahead, set up energy. Gets us 1/2 K, and it gives us X. Okay, so for that we get 0.13, and that is joules. So it wants us to use energy conversion to find the speed. So PE spring is equal to KE at equilibrium. So we can use the PE that we found, 0.13, equal to, and we know our KE function is 1/2 mv squared. And we can just plug everything in and solve. So the mass it wanted us to use 0.1. We're solving for V. So we can go ahead and solve for V squared. So we get 2.6 is equal to V squared square root 1.6 like 1, and then that's meters per second. Okay, so that is the speed at equilibrium. Alright, moving on to the final part, part E. Let's see. Grab another paper. Okay, part E. Okay, so it wants us to calculate a new speed, because now the mass is being stretched twice the previous length. So first part, find the new speed, and then clearly state the relationship between the distance stretched and the maximum velocity at equilibrium. So first, let's find the new speed. So again, we can use the same thing we did here, really, just obviously different numbers. So So we have found the new speed with the new stretched length. And on to the second part of that question. Clearly state the relationship. So, okay, so we need to look here at the answers we got. Let's see. Okay. Trying to make sure you can see everything. Okay, so looking at the answers that we got here, we can see that when you stretch the spring double, stretch the spring double, your velocity doubles. So that means as your x increases, your v will increase as well, because it is a linear relationship. And we can prove this. So we can do some math to prove this. So let's go ahead and write out what we were doing. Alright. Halves cancel out. And when you solve for v, what you get is and this together is a constant, because you have your k constant and your mass, which doesn't change, is equal to v. So you can kind of ignore it because it is a constant, but what you have is your x equal to v in a way. So that shows that if this increases, this will also increase. And that concludes FRQ 5.